So we left off last time at definition 36. So suppose phi is a ring homomorphism going from R to R hat. Then we define the kernel of phi to be the inverse image of 0, where 0 here is the additive identity in R hat. Well, by theorem 35, we note that phi inverse, if phi is a ring homomorphism, phi inverse of S hat is a subring of R whenever S hat is a subring of R hat. And the point being, 0, sure enough, is a subring, and so its inverse image, which is the kernel, must be a subring of R, right? So since 0 is a subring of R hat, and phi inverse is a ring homomorphism, phi inverse of 0 is a subring of R. All right, let's go on to theorem 39. Suppose I have a ring homomorphism. Then the kernel of phi, which by the way I have just said is a subring of R, is equal to 0 if and only if phi is injective. So let's see how that goes. Injective, recall, means 1-to-1. All right, so now I'm going to use 0 hat to indicate the additive identity of R, and 0 to indicate the additive identity of R. Right, so 0 hats in R hat, 0's in R. Now, since I know it's a ring homomorphism, hence a group homomorphism, it takes the identity to the identity, so phi of 0 is 0 hat. That's enough to tell me that, sure enough, 0 is a subset of the kernel, because what does the kernel mean? It's anything that gets mapped to 0 hat. So I've got that side containment. I just have to show the other side, that the kernel contains 0, or rather that the kernel of phi is contained in 0. All right, so what do? I choose something in the kernel. I need to show that it's in here. Well, to be in here, it's got to be 0, right? So pick an arbitrary thing in the kernel. Then phi of R is, since it's in the kernel, it's equal to 0 hat. But guess what? Phi of 0 is also 0 hat. And it's assumed that phi is injective. So if phi of R is the same as phi of 0, that says R equals 0. And sure enough, I've just shown that the kernel of phi is the set 0. All right, now I'm going back the other way. Suppose the kernel of phi is the set 0, and I need to show phi is injective. All right, so if the kernel of phi is 0, suppose I have a phi of R1 equal to phi of R2. I need to show R1 is equal to R2. Well, but this implies adding a minus phi of R2 to both sides, that phi of R1 minus phi of R2 is, of course, this is 0, right? 0 in R hat. But phi is a homomorphism, so phi of R1 minus phi of R2 is the same as phi of R1 minus R2, but I just said that was 0 hat. What does that mean? That R1 minus R2 has to be in the kernel. But my assumption was that the kernel is just the element 0. So that tells me R1 minus R2 has to be 0. Adding R2 to both sides tells me R1 has to be R2. QED, we're done. And finally, theorem 40. Suppose phi is a ring homomorphism going from R to R hat. then we claim the kernel is an ideal in R. Now, by corollary 37, I already know it's a subring. All right, so what more do I have to show that it's an ideal? Well, an ideal is a subring that has the stronger closure. That is, if I pick anything in R and anything in the kernel, R times K has to be the same as K times R, has to be in the kernel. All right, so now I'm going to prove that KR is in the kernel. Well, what does it mean to be in the kernel? It means that when I hit it with phi, I should get 0. Right? So let's look at phi of KR. Well, phi of KR is phi of K, phi of R. Okay, but what's phi of K? Well, remember, K was chosen to be in the kernel. So if K is in the kernel, phi of K has to be 0 hat. So we have 0 hat times phi of R, but guess what? The additive identity of the ring times anything in the ring we proved is the additive identity again. All right, so therefore I've just shown that phi of KR is in fact 0 hat. What does that mean? That KR is in the kernel. All right, and now I'm going to claim that a similar argument can be used to show phi of RK, or rather RK is in the kernel. And I'll leave that up to you.